Okay, these are helpful hints on the Chapter 8 homework problems. There's some real tricky ones in here, but hopefully with the hints I give you, if you get stuck, these will get you unstuck. Let's start with problem 1, center of gravity. 3 point mass particles are located in the plane, and they give their kind of xy coordinates and the mass of each one. How far is the center of mass from the three particles from the origin? So we haven't done a lot of work with center of mass of objects that aren't continuous. We talked about the center of mass of a disk being at its center of symmetry. Here we're thinking of our object as just being the 3 point masses grouped together as a unit. But we use the definition of center of mass. The x-coordinate of the center of mass is m1 x1 plus m2 x2 plus m3 x3, all divided by the total mass, the sum of the masses. And the same thing for the y-coordinates with the y's in there. So you find the x-coordinate of the center of mass, find the y-coordinate of the center of mass. If you leave the numbers in centimeters, then those coordinates of the center of mass will be in centimeters. And then to find the distance, how far it is from the origin, what we would do is take the square root of the sum of the square of x center of mass squared plus y center of mass squared. Take the square root of that, and you'd get the distance of that point from the origin. 2. A high-speed sander has a disk of radius so many centimeters and rotates about its axis at a constant rate given in revolutions per minute. Determine the angular speed of the disk in radians per second. So the 690 revolutions per minute is an angular speed. It's just not in our SI units. So to convert it, we do the usual unit conversion where I have to convert revolutions to radians and minutes to seconds. So I multiply that 690 times 2 pi radians over 1 revolution. That's a factor of 1 there because the numerator and denominator are the same. And then I multiply by 1 minute over 60 seconds. That's another factor of 1, since the numerator and denominator are the same. That gives us, after canceling the units, that the result will be in radians per second. 2. Determine the linear speed of a point 1.39 centimeters from the disk's center. For this, we use the conversion between linear and angular speeds. And the relationship is v equals r omega. The r we want to use here is the distance of that point from the center. You don't want to use the radius of the disk, which is bigger in this case. So v equals r omega. We just found omega above in radians per second. So if we multiply by the 1.39 centimeters, or I guess since we want the answer in SI units, we would multiply by 0.0139 meters, then we would get the speed of that point in meters per second. Part 3, determine the centripetal acceleration of a point on the rim in meters per second squared. So we're going to do the usual thing, v squared over r. So we need the speed v of a point on the rim. That's not the same as the speed that we found in part 2. So we need to calculate the speed of a point on the rim. So again, we can use v equals r omega. Now we're going to use r, the radius of the disk, which for me is 4.09 centimeters. I would put it in meters, and then I'll get that speed in meters per second. And then calculate v squared over r, where again r is the radius of the disk, and that would give us the centripetal acceleration in meters per second squared. Part 4, determine the total distance traveled by a point on the rim in 2.62 seconds. So in this case, if we know the speed of a point on the rim, that's the answer of part C, we can just use speed equals distance over time. We know the speed and we know the time, that's 2.62 seconds for me, so we can calculate the distance it goes. That's just the distance over time trick, if you like. Problem 6, rotating disk. A disk of a certain radius rotates at a constant speed in revolutions per minute about its central axis. Determine the angular speed. So that's just like the first part of the previous problem. We already know the angular speed in non-SI units. We're going to convert to SI units by multiplying by 2 pi radians over 1 revolution and 1 minute over 60 seconds. Do that and you'll get the result in radians per second. Part 2, Determine the linear speed of a point so far out from its center. Well, this sounds like kind of a repeat of the previous problem. So we use v equals r omega with this r and the omega we just found in the first part. Determine the radial acceleration. Well, radial acceleration is the same thing as centripetal acceleration of a point on the rim. So we need to separately find the speed of a point on the rim. That's not the answer to part 2. And then use v squared over r, where r is the radius of the disk. If everything's in SI units, then the result will be in meters per second squared. And finally, the distance the point on the rim moves in 2.52 seconds. That's v, which we know, the speed of a point on the rim of the disk we just found at the beginning of part 3. V equals distance over time. We know the time and we know v, so we can calculate distance. Problem 10. The turntable of a record player rotates initially at 33 revolutions per minute and it takes so many seconds to come to rest. What's the angular acceleration of the turntable, assuming the acceleration is uniform? So this is a constant angular acceleration, so we can use our kinematics equations. One of them says omega final is equal to omega initial plus alpha times t. So we have, in this case, it's starting out, this would be our omega initial, 33 revolutions per minute. We should convert that to radians per second, just like we've been doing in the above problems. So omega initial is this, omega final is 0, it's coming to rest, right? We want alpha, and then the t it takes is 25.55 seconds for me. So we can solve for alpha, put everything in SI units, we'll get alpha in radians per second squared. Part 2, how many rotations does the turntable make before coming to rest? So in this case, again, once we've converted to radians per second, we have omega final and omega initial. We can use our third kinematics equation, omega final squared equals omega initial squared plus 2 alpha times delta theta. So if I put in my omega final and the omega initial in SI units, right? Put in the alpha we know, that's what we found in part 1. We can solve for what delta theta is, and delta theta would be in radians. What we want then, so we're almost there, we want delta theta, that's how far it rotates, but we want that in revolutions. So if we know it in radians, then we can multiply by 1 revolution over 2 pi radians, because the numerator and denominator are the same. That would get it in revolutions. Part 3, if the radius of the turntable is 10 centimeters, what's the tangential acceleration of a point on the rim at t equals 0? So in this case, we've got an alpha, and the relationship between tangential acceleration and alpha is a tangential equals r times alpha, where in this case we should use the radius of the turntable, so 0.1 meters times alpha would give us the tangential acceleration of a point on the rim. And if we had it in SI units, that would give us the tangential accelerations in meters per second squared. Here we have to convert to centimeters per second squared. Problem 13, a bicycle wheel of radius 0.27 meters rolls down a hill without slipping. Its linear velocity increases constantly from 0 to 7 meters per second in 2.5 seconds. What is its angular acceleration? Well, in this case, I can use the relationship for rolling without slipping between the speed of the axle and the angular speed of the rotations about the axle. That's v axle equals r omega. So in this case, we know omega initial is 0. Omega final is going to be, well, we use v equals r omega using this v and solve for omega final to get omega final in radians per second. And then to find the angular acceleration, we're going to use omega final equals omega initial plus alpha times t. We know omega final and omega initial. We know t, so we can solve for alpha in that equation. When we put everything in SI units, then the answer will be in radians per second squared. Part 2, through what angle does the wheel turn in 2.5 seconds? This sounds like a kinematics kind of problem, and again, probably the easiest way to proceed is to use omega final squared equals omega initial squared plus 2 times alpha times delta theta, and the alpha we've already figured out above, and so it looks like we know everything. We figured out what omega final was above too, so we can figure out then what delta theta is, and if we put everything in SI units, delta theta will be in radians, so that's ready to put in for this particular problem. Part 3, how many revolutions does it make? Well, we've got the angle in radians, so we're just going to use the relationship, just convert units from radians to revolutions. So multiply the radians value times 1 revolution over 2 pi radians, and that will give us the answer to part 3. Problem 16, a rod can pivot at one end and is free to rotate without friction about a vertical axis as shown. So this rod kind of wants to fall with no other forces on it but gravity, right? A separate force is applied at the other end, so it's pushing up and to the right, so kind of, in the direction that might hold it aloft if it were just the right force. If F were to be applied perpendicular to the rod, so instead of pushing up at an angle up and to the right, we use the same force and pushed exactly perpendicular to the rod, at what distance should we apply that force? In other words, should we push here perpendicular, or here, or in here perpendicular? At what distance from the rotation axis should we push with the full strength of F perpendicular to get the same torque? And the idea is, one way to calculate the torque here is, L times F times the sine of that angle theta. That angle theta is the same as the angle theta the way I usually drew it over here. And one way to break that up is to say, well, instead of thinking of it as F times sine of theta separately multiplied by L, we could think of it as the full F multiplied by L sine theta. That's F times the moment arm, that are perpendicular. So L times the sine of theta is the appropriate distance we push on an object to get the same exact torque that this configuration would produce. So I'm seeing that in my version as answer 4. 17. A uniform horizontal rod of mass 3 kilograms and length 1 meter is free to pivot at one end. The moment of inertia of the rod about an axis perpendicular to the rod and through the center of mass is given by 1/12 ml squared. Now we should be careful here. That is not the moment of inertia of this rod about this pivot. That's the moment of inertia about the center of mass. There's a result that we didn't really talk about, or I didn't talk about in the videos, that allows you to use that to get to the end. But we already know the answer for the end. We can find that in our table of moments of inertia in the book, or the one I used in the videos, and that is 1/3 ml squared. So the I we need for this rod pivoted about one end is 1/3 ml squared, if I remember correctly. Okay, if a 5.3 Newton force at an angle of 85 degrees as shown acts on the rod as shown, what is the magnitude of the resulting angular acceleration about the pivot point? So I'm going to use torque equals I alpha. In this case, it's torque net, but in this case, I don't think there's supposed to be any gravitational, this is in the absence of gravity, or maybe it's rotating horizontally. So I better read this carefully to make sure that's the case. Yeah, I think there's no gravity trying to pull this down, so we don't have to worry about gravity in this problem. So the net torque is just going to be F times the sine of 85 degrees, right? And we're given F there. And that's equal to I, which is 1/3 ml squared. Here's our m. L is 1 meter for me, times alpha. And then solve for alpha. That if you put everything in SI units, you'll get alpha in radians per second squared. Problem 18, hinged rod with mass. Here's a rod. We've got its mass, it's a uniform rod, we've got its length, its mass, frictionless pivot at one end, and the rod is released from rest at the angle shown. What is the angular acceleration of the rod immediately after it's released? So in this case, it looks like gravity is playing a role in this particular problem, because otherwise it wouldn't rotate at all. So I think gravity is supposed to be acting in this problem. Again, it's unclear in this previous problem whether there's always a possibility that they might be thinking that gravity is acting, but we'll assume not for that one. In this case, clearly it's assumed to be acting because it's going to start, otherwise it wouldn't accelerate at all. What's the angular acceleration of the rod immediately after it's released? Well, again, this 1/12 ml squared is not the appropriate moment of inertia for pivoting around one end. So we want to use the one from the table, 1/3 ml squared. That's our I, and we're going to use torque net equals I alpha to solve for alpha. We just need torque net, and in this case there's only gravity acting on it. We'll use our usual simplification that the full weight force is acting at the center of mass of this rod, and that's because it's a symmetric object, that's at the center of symmetry. So we're going to pretend that the full 5 times 9.8 acts halfway across the rod straight down. So it looks like we need to do 5 times 9.8 times what is the moment arm? Well, that's this distance here, and that would be 3 meters times the cosine of 27 degrees would give us this moment arm for that force that's acting downward there. So that torque equals I, which is 1/3 ml squared, times alpha. Solve for alpha. Problem 19. A light string, 0.6 meters long, is wrapped around a solid cylindrical spool with a radius of 0.07 meters and a mass of 0.8 kilograms. A 1 kilogram mass is then attached to the free end of the string, causing the string to unwind from the spool. So this sounds like a problem we did in a worksheet in the video that you should have gotten by watching the video. What's the angular acceleration of the spool? So we're going to use this one. The solution method is just like we did on that worksheet. We're going to do separately F net equals ma along the vertical direction for the free body diagram of just the falling mass that's moving linearly, and then also torque net equals I alpha for the spool, where the net torque is just the force, the tension in the string, times the radius of the spool, right? That's going to be force times moment arm, and that would be the net torque, and set that equal to I for a uniform cylinder about its axis of symmetry. I think that's 1/2 mr squared. So torque net equals I alpha, and then I can replace the A in the linearly moving mass with something related to alpha. Replace that A in F net equals ma with A is equal to R times alpha, because the tangential acceleration of a point on the rim is R alpha, and the tangential acceleration of a point on the rim is the same as the linear acceleration of the mass as it moves down. When we do that, we'll get two equations and two unknowns. The two unknowns will be tension and alpha, so we can solve for t equals and substitute and get an equation that only involves alpha. It is just like the problem we did on the worksheet in the videos. Part 2, how fast will the spool be rotating after all the string is unwound? Well, the string is 0.6 meters long, so that means the tip on the edge of the spool has moved through a distance of 0.6 meters. We can use our relationship between arc length and angle to say an arc length of 0.6 meters corresponds, S equals R times theta. S is 0.6 meters, R is 0.07 meters. Solve for theta. That gives us the change in angle. And I'm losing track of what we were asked for here. How fast will the spool be rotating after all the string is unwound? So we know what our delta theta is, and we know omega initial is 0. We want to find omega final. So we can use our omega final squared equals omega initial squared plus 2 alpha delta theta. Through some effort, we found alpha above. We just discussed how to find delta theta, and we know omega initial is 0, and we want to find omega final by taking the square root there. And if we put everything in SI units, that'll be in radians per second. Problem 21. A 20 kilogram mass is attached to the cord, wrapped around a wheel with radius 10.1 centimeters. The acceleration of the mass down the inclined plane, which is frictionless, is 2.1 meters per second squared. And there's no friction in the wheel. Find the force in the rope. Most people would call that a tension in the rope. To find the tension in the rope, that sounds like we could just do a free body diagram only for this sliding mass, and this brings us way back to chapter, I don't remember, 3 or 4, whenever we first did F net equals ma for one-dimensional motion. We know the acceleration of this object, and we know the forces acting on it, right? There's a normal force, there is a tension force acting along the plane, and there's a weight force going straight down. So we could do F net x equals max. We know m, we know ax. Let's let x be up the plane, or sorry, down the plane. That would probably be easier in this case. And you figure out what there's, so the tension force would come in with a minus sign if I take plus x to be down the plane. The weight force component along the plane direction would end up with a positive sign, and we could solve for the unknown tension in that case. Part 2, find the moment of inertia of the wheel. Well, here I can apply torque net equals I alpha for the wheel. If I know the acceleration of the box, that's the same as the tangential acceleration of a point on the tip of the wheel, then I can use A tangential equals R alpha to find alpha for the wheel. And then I can apply torque net equals I alpha. We now know what alpha is. The net torque, well, the only thing applying a torque to this wheel is the tension force, right? Otherwise it wouldn't be rotating at all. So the net torque is just the tension in the string. It's being pulled tangent to the radius of the disc, so its moment arm is just the radius of the disc. In my case, that's 0.101 meters. So torque net is tension times the radius of the disc equals I alpha. Solve for I in that case. That's the answer to part 2. Part 3, find the angular speed of the wheel 3.1 seconds after it begins rotating. Well, again, we found in the process of doing the previous part, we found out what alpha was in radians per second squared, and therefore we can do a little kinematics calculation. In this case, it looks like the appropriate one to use is omega final equals omega initial plus alpha times t. Here's our t. We know alpha. We know omega initial is 0 if it starts from rest, and we want to calculate what omega final is. Problem 24. A circular disc, a ring, and a square have the same mass and the same width in the sense shown there of 2r. Find the moment of what's the ordering of the moments of inertia? How would we order them? Which one has the biggest? Which one has the smallest? Remember, with moment of inertia, the idea is if you have the same bits of mass, but the mass is farther away from the rotation axis, and in this case, reading the details here, the rotation axis is at the center of the ring, the center of the disc, and the center of the square. If we have the same mass in all the purple regions shown here, in which case is the mass farthest away from the axis on average? And the idea is, well, look, some of the mass is in close to the rotation axis for the disc here. All that mass is pushed out to the edge of the circle here, so this one's going to have a greater moment of inertia, because when I add up all those m times r squareds, the r's are going to be bigger on average in this case than this case. So the ring is bigger than the disc. Furthermore, the square has a bigger moment of inertia of the ring, because to make the square out of the ring, you'd have to take some of those bits of mass and push them even farther into the corners. And so the square's moment of inertia would be the biggest, then the ring, then the disc. And it looks like I'm seeing my answer number 1, coincidentally, is the correct answer in my version. There's other options up here, but for me, the first answer looked correct. Problem 25. Consider two bicycle riders A and B. The two riders have equal masses and their respective bicycles have similar frames. Okay, so the riders and the bicycles themselves have the same mass, so everything's got the same mass. The wheels of the two bicycles have the same mass and equal radius. So the only difference between these bicyclists and their bicycles is how the mass is distributed on the wheels. In one case, all the mass is out at the edge of the rim, whereas in the other case, it's distributed across a disc. They're sort of like uniform disc wheels. That's biker B. The two cyclists travel at the same speed on level ground. They approach a low hill and decide to coast up instead of hard pedaling. At the top of the hill, which of the two bikes will have a larger speed? Assume no friction, no air resistance, and all the wheels roll on the ground without slipping. So the idea here is that if they're moving at the same speed initially, whichever wheel has the larger moment of inertia will have more rotational kinetic energy stored in it. So if they're moving at the same speed, remember rotational kinetic energy is for a, of course, the rider and the frame have the same rotational kinetic energy because their masses are the same, but the wheels aren't necessarily that way. Remember, if an object is rotating around its center of mass, while the center of mass moves, we do the rotational kinetic energy, the total kinetic energy is 1/2 I omega squared plus 1/2 mv center of mass squared. And in this case, the I's are going to be different. So whichever one of these wheels has the bigger moment of inertia will have more kinetic energy stored in it if they're moving at the same speed. And that's bigger for wheel A because the mass is further out. So there's more kinetic energy in the initial state for rider A. If they coast up to the top of the hill, which will have the larger speed? Well, think about it this way. A has more kinetic energy to start with than B. That means if they rode up the hill until they came to rest, A is going to end up going farther because it has more kinetic energy that will be converted into potential energy when all the kinetic energy runs out. In other words, when they come to rest. So A would go farther up a hill where they didn't reach the top of it. And what that means is that at every point on the hill up to that point, A would have been going at a faster speed than B. B would always be going slower because A is always going faster in order to make it up farther. So that means A is always moving faster, and therefore at the top of this hill, they haven't really run out of speed, either one of them, but A would have been moving faster at the top of the hill than B. Not sure what selection that is. There's a lot of choices here. It looks like the answer is bike A, and it's because the wheels have a larger moment of inertia. So that looks like answer 9 in my version. Rotation of a solid disk. Uniform solid disk of radius 5.2 meters and mass so many kilograms is free to rotate on a frictionless pivot through a point on its rim. Now we don't have this moment of inertia for a disk or a cylinder rotating about an axis perpendicular to the disk and through the rim. We only know it through the center. There's a result we didn't talk about called the parallel axis theorem. It's probably, if I remember correctly, it's probably in G and Colley, but I never talk about it in Physics 110. It's just too much. In any case, we could use that to figure out what it is. I'm just telling you the answer in this case. It's 1/2 mr squared about if the axis is perpendicular to the center. If it's out here at the edge, it's 3/2 mr squared, where r is the radius of the disk, or 1.5 times mr squared. That's the moment of inertia for a disk pivoted for rigid rotation about a point on its edge where the axis is perpendicular to the disk. All right, if the disk is released from rest in the position shown by the solid circle, what's the speed of the center of mass? In other words, how fast is this moving through space, that point at the center, when it reaches the lowest position, the position shown by the dashed version there. Here we can use conservation of mechanical energy in between release from rest and the moving point here. And the idea is, well, I'm going to take my system to be the disk plus Earth, where gravity is an internal conservative force. There are no other forces doing work on this disk as it goes down. I mean, you could think of the only other force on the disk is the pivot, but that point at which the force is being applied isn't moving through space, and so therefore it does no work. So the net work done by external forces is 0, and that's equal to the change in kinetic energy plus the change in potential energy. So 0 equals, and this is a body moving rigidly about a fixed axis, so we just use that 1/2 I omega squared for the kinetic energy. So 0 equals 1/2 I omega final squared minus 1/2 I omega initial squared, where omega initial is 0, plus change in potential energy is m times g times delta y of the center of mass, and delta y of the center of mass is in between here and here. It goes down, the center of mass moves down by exactly 1 radius, so delta y of center of mass would be minus 5.2 meters in my version. So put all that together, solve for omega final. Once we've got omega final, this point at the center of mass is moving rigidly about the pivot point, so we can use v equals r omega to figure out what the final speed is down here. We use r omega final, v equals r omega final, and here the distance r from the rotation point is just 1 radius to solve for v of the center of mass at that final point. If we put everything in SI units, the answer will be in meters per second. What's the speed of the lowest point on the disk at the dash position? So again, if we know our omega final, the only difference in this part would be I'm going to use v equals r omega, but now the r I use is 2 times 5.2 meters, and so that will give me a speed that's twice as big as the part above that we just finished. Ooh, this is a slog. Okay, last problem in 2 parts. A solid sphere of radius 19 centimeters positioned at the top of an incline. We're given the angle of the incline. The sphere is released and it moves down the incline. It rolls without slipping. It moves a distance of 3.2 meters down. Okay, they give us the moment of inertia of the sphere about the center is 2/5 mr squared. Find the speed of the sphere when it reaches the bottom of the incline. So in this case, there's some rotational kinetic energy and some translational kinetic energy. So we're going to, again, take our system to be the sphere plus the Earth. Gravity is internal, but we could take the all the forces from the plane on the rolling ball to be external, but neither of those do any work. The normal force doesn't do any work, and in the slides I talked about how the friction force, which is necessary to roll without slipping, also doesn't do any work. So W net equals delta KE plus delta PE. W net is 0 by external forces, okay? And that is equal to delta KE, so we're going to do KE final minus KE initial, where KE is 1/2 I omega squared plus 1/2 m v center of mass squared. Okay, do that final minus initial for those two things. And then for the change in potential energy, we would do capital M times G times delta Y, where delta Y is going to be a negative number minus L. Let's see, if we're given the angle here, that would be L times the sine of 29 degrees would give us, that negative number would be our delta Y in that case. Okay? Now, when you write down the equation, you're going to have 5 terms in there because we have 4 terms just from the change in kinetic energy. In this case, all the initials go to 0, so V initial and omega initial are 0. And we can use the relationship between V and omega for rolling without slipping. V center of mass is equal to R times omega at all points in time if it's rolling without slipping. So that means I can change out my omega final for a V center of mass final in that expression. And then I will have an equation that only depends on V center of mass final. I'm going to have to do a little grouping together of terms to solve for V, center of mass final, but should be able to solve for it and put everything in SI units. It'll be in meters per second. Part 2, find the speed of the sphere if it reaches the bottom of the incline by slipping frictionlessly without rolling. So in this case, it would be moving as a particle. So we can't use the same equation we had in the previous one. We would still use net work by external forces is delta Ke plus delta Pe, but in this case, it only has translational kinetic energy. So we would just have for change in kinetic energy, we would just have 1/2 mv final squared minus 1/2 mv initial squared. And we will find out that at the bottom, it's moving faster than it was in part 1, because in part 1, part of the kinetic energy was stored in that rotational motion and part of it in translational, whereas in the second case, the same change in potential energy all goes into just translating through space. So your answer should be bigger in part 2. And that is that. That was quite a collection of homework, but there are a lot of ideas in this chapter. Many of you talked about how there were confusing issues. Practice makes perfect here, and there are just a lot of types of problems that we need to practice with. So we're going to be doing a lot of practice in the coming week. Thanks.